Okay, now let's continue with the same example as we finished in the previous installment of this lecture. So I'm looking at the sequence Sn equal to 1 over 2 to the power n. In this first example, we constructed what looked like a subsequence. It turned out not to be, because some terms, even though all of the terms appear in the original sequence, some of the terms are not in order, so what we got is not a subsequence. Now, what about something like this? So if you have 1/4, 1/16, 1/64, 1/256, would that be a subsequence? And in this case, it's easy to see that the answer is yes, because 1/4 is 1 over 2 squared. So that means that 1 over 2 to the n, 1 over 2 to the second power, so n is equal to 2 for 1/4. Likewise, 1 over 16 is 1 over 2 to the fourth, and 1 over 2 to the fourth is S4. 164, 1 over 2 to the sixth, so it's S6. 1 over 256 is 1 over 2 to the eighth, so that's S8. So if I look at this, then that means that I got a sequence which includes all elements of the form S2k, and they do appear in order, because function 2k is an increasing function from integers to integers. So what I got here is a subsequence. One comment that I would like to make: if I choose to select all elements of my original sequence in order, then I still get a subsequence, but that subsequence is a original sequence itself. So in a sense, you didn't do anything. It's a trivial subsequence. Why we might be interested in subsequences? Because not so much in this case 1 over 2 to the power n, where 1 over 2 to the power n is a sequence which goes to 0. So as we'll see actually pretty soon, if the sequence converges to 0, for example, then it should be clear that all subsequences of that sequence also must converge to 0. Right? Because as n gets bigger, as n gets smaller, so it doesn't matter if you look at the sequence or subsequence, the outcome is always going to give you the same limit. It's not the same for sequences like this one here, where you have sequences keeps oscillating between -1 and 1 as you go to infinity, so that sequence that I circled is certainly not convergent, but it contains subsequences like all ones, and all ones clearly is a sequence that converges to 1. So my originally bad subsequence, which was oscillating, bad in terms of its behavior as n goes to infinity, it contains a subsequence that converges. If somehow I overlook some of the elements of my original sequence, then I get convergence. Likewise, the subsequence that consists only of -1s would be convergent. Subsequence as for k, which consists only of 1s, would be convergent, and so on. But actually, that next subsequence, where I chose 2 -1s and 2 1s, 2 -1s and 2 1s, this subsequence clearly does not converge because it oscillates. And somehow later on in the future, it would be useful to sometimes work with subsequences rather than original sequences. And when you choose a subsequence, you typically want to choose something that converges. All right, so let's now discuss a couple of theorems, which are going to be again useful in the future. So first thing that I would like to do is I want to prove a simple theorem which states the following. So if I have this strictly increasing function from positive integers to positive integers, right, based on which I'm going to build my subsequence, then it turns out that I can guarantee that this function, strictly increasing function, will always have n of k greater or equal than k for all k greater or equal than 1. Which is kind of, again, it should be clear when you think about it. If you move along the subsequence by skipping elements of the original sequence, you should be able to go to infinity faster than you did in the original sequence. But now let's prove that again, because we're proving something for every k greater or equal than 1. We should use induction. And then we need to do a base step. So the base step is simple in this case because 1 is the smallest possible positive integer that I can have. And if my function is n of k is integer valued, then I'm guaranteed that n of 1 is greater or equal than 1, just because 1 is the smallest possible positive integer. So then I'll do an induction step. An induction step says, let's suppose that the k statement is true, n of k is greater or equal than k. And I need to prove something similar about k plus 1. Well, what do I know in this case? I know that my function n of k is strictly increasing, so it means that n of k plus 1 must be strictly bigger than n of k. But if an integer n of k plus 1 is bigger than integer n of k, that means that n of k plus 1 should be at least n of k plus 1, right? It can be equal to next integer after n of k, or higher. So n of k plus 1 must be greater or equal than n of k plus 1. But I already assumed that n of k is greater than k. So if I replace n of k by k, then I'm going to get something smaller. But that's exactly what I wanted to show. N of k plus 1 is greater or equal than k plus 1. So I'm done. All right, next theorem that I'm going to be interested in is going to be something like this, which should also be fairly intuitive. Let's suppose that I have a sequence which is not bounded from above, right? Which means that the sequence can have arbitrarily large elements. So the claim is that in this case, I can find a subsequence of this sequence that will monotonically go to plus infinity. So I can find a sequence which is subsequence, which is monotone increasing, and it has a limit then infinity, right? Because if a sequence is monotone increasing, it must go to infinity. So how can we prove this? And actually, there is a second statement here. If a sequence is unbounded from below, then likewise I should be able to find a monotone decreasing sequence which will have a limit minus infinity. So let's prove one of these statements, and the second one would, as usual, be symmetric. So let's look at the sequence which is not bounded from above. Then I can always choose n1 to be equal to 1, right? The first element of my subsequence, I can just choose the first element of the original sequence. And then I'm going to consider a number which is a maximum of 2 and the value of that first element of the original sequence. Right, so that is going to be a number. And because my sequence is not bounded from above, I know for sure that this number is not an upper bound on the original sequence, right? So this number up here, maximum of 2 and the first element of the sequence, is not going to be an upper bound on my sequence. Why? Because the sequence is not bounded from above. So because it's not bounded from above, then I should be able to find another term in my sequence, which I'm going to, with which I can associate the index n2, right? So that n2 should be to the right of the first term, to the right of n1. So n2 must be greater than 1. And again, because this guy is not an upper bound, then Sn2 is bigger than this maximum. Okay, so if Sn2 is bigger than a maximum of 2 and Sn1, if it is bigger than the largest of these two numbers, it must be bigger than 2 and it must be bigger than Sn1, right? If something is bigger than the maximum, then it must be bigger than all things, the maximum of which I'm computing. So that means that Sn2 must be greater than 2 and Sn2 must be greater than Sn1. And now I'm going to use induction. So I'm going to assume that similar statements are going to be true at the kth level, that I have Snk which is bigger than Snk minus 1, right? So I'm able to construct my subsequence up to the nkth element, and I still maintain this set of inequalities. Snk is bigger than Snk minus 1, and at the same time Snk is greater than k, right? These are these statements for 2 being replaced by k. Okay, so then again, if I take a maximum of Snk and k plus 1, that certainly is not an upper bound because my sequence is not bounded from above. And because it's not an upper bound, then I should be able to find an element nk plus 1 with an index nk plus 1 such that this element is bigger than this maximum. And if this element is bigger than this maximum, it must be automatically bigger than both of these things, the maximum of which I'm taking. So Snk plus 1 must be greater than Snk, and Snk plus 1 must be greater than k plus 1. Well, so then induction shows that I can construct a sequence which is going to satisfy these conditions, that Snk is always increasing, right, because each next element is bigger than the previous one, and Snk plus 1 is bigger than k plus 1. This guarantees that the subsequences Snk is increasing, and this guarantees that Snk plus 1, that Snk goes to infinity. Why? Because if, let's look at this here, if k goes to infinity, then Snk is bigger than that, so Snk must go to infinity. So that means that we proved this claim that the subsequence that I constructed is both increasing and it goes to infinity. So it's a monotone increasing subsequence of my original unbounded sequence, right? So every unbounded sequence, therefore, contains a monotone sequence which converges to plus infinity. All right, so now let's try to prove a similar result for the case when the sequence is bounded. And the analog of what I just proved can be formulated in the following way. Let's say I have a sequence Sn, and I'm asking a question, does that sequence contain a subsequence which converges to some given t, which is a real number? Right? So again, remember that from any sequence I can extract infinitely many possible subsequences, and the question is, if somebody gives me a number t, will I be able to prove that the subsequence actually, that the sequence contains a subsequence which goes to that t? And this theorem gives us a criterion for this. It says that there will be a subsequence that converges to t if and only if the following statement is true. That if I take an epsilon neighborhood of t, right, then this neighborhood must contain infinitely many elements, regardless of what epsilon is, right? So you take t, you go down and up from t by epsilon, and you look at this interval, right? So you have an interval. Let's draw a small picture here. You have an interval from t minus epsilon to t plus epsilon. And basically, what I said here means that in this interval there would be infinitely many terms, elements of my sequence. And it doesn't matter how small epsilon is, there are always infinitely many elements there. And so then it kind of stands to reason, right? So if in any neighborhood of t, right, doesn't matter how small it is, I can find elements of my sequence, then I should be able to select elements of a sequence in such a way that it will generate a subsequence that converges to t. And that is what I'm about to prove. Okay. So we have this if and only if statement, so that means that we have to prove this in two directions. First of all, we have to assume that there exists a subsequence like this, and then we have to prove that a set like that is going to be infinite. It will contain infinitely many elements for any epsilon. And then we have to do the opposite. We have to assume that all of this is true and then prove that there exists a subsequence converges to t, that converges to t. So let's suppose that such subsequence exists. So we're proving this in one direction. Well, if a subsequence converges to t, what does it mean? Now, remember that subsequence is labeled not by n anymore, but by k, right? Because k goes from 1 to infinity through all integers, right? So k is 1, 2, 3, 4, 5, 6. And then nk tells me which terms of my regional sequence I should take. So, all right, so at this stage I can forget where this subsequence came from. It just, I have this s and k, which in fact I can think of as tk. And the sequence tk converges to t. Now what does it mean? It means that by definition of a limit, for any epsilon greater than 0, there should exist, as usual, capital K in R, right? Typically I call it n, but in this case the index is k. So I'm going to call this capital K, such that s and k minus t is less than epsilon for any key k which is bigger than capital K. All right, but how many little k's like that do I have? Right, S and K itself is a sequence. It's subsequence of a regional sequence, but it itself is a sequence. So in this case, as any sequence, it contains infinitely many elements. So that means that how many elements with K are there with K bigger than capital K? The answer is infinitely many. So that means that this set, right, set of SNs, which differ from t by less than epsilon, that set will contain infinitely many elements. And because this is true for any epsilon, right, then I prove the theorem, the statement going forward. So now I have to prove the statement going in reverse. So instead, I'm going to suppose that if I pick any epsilon greater than 0, then this set will contain infinitely many elements. Well, how else I can write this set? I can write this as a set of all SNs, right, without using absolute value sign, set of all SNs where Sn minus t is between minus epsilon and epsilon. And because the original set has to have infinitely many elements, then a circled set also has to have infinitely many elements for any epsilon greater than 0. Okay, fine. But what does it mean to have Sn that lie in a set like this? Well, that means one of the two things. Either Sn is between t minus epsilon and t, or Sn is between t and t plus epsilon, right? And furthermore, well, actually before furthermore, so that means that if I pick a particular epsilon, either this set or that set or both will have to contain infinitely many elements, right? Because a union contains infinitely many elements, union of two things, union of two sets contains infinitely many elements. It means that at least one of those sets will have to have infinitely many elements. Not only that, but also as I make epsilon smaller, then sets like that will be so-called nested, right? Because if, for example, there are infinitely many SNs between t minus 1 and t, there should be infinitely many SNs between t minus 1/2 and t. So from this, we can make a conclusion that either this set has infinitely many elements for any epsilon, or this set has infinitely many elements for any epsilon. So either between t and t plus epsilon I have infinitely many SNs, or between t minus epsilon and t I have infinitely many SNs. And so I then have to consider both cases separately, and those two cases can be treated in exactly the same way, in a typically this mirror way, like infimum and supremum, right? If you proved some statement about infimum, then there is a symmetric way to prove something about the supremum. It works in the same way here. So for that reason, I'm only going to consider the case when between t minus epsilon and t, I have infinitely many elements for any epsilon greater than 0. And so the way it works is going to be like this. I'm going to first select epsilon, I'm going to call it epsilon 1 equal to 1. And because for any epsilon, the set here contains infinitely many elements, I should be able to choose one element, like this, right? If there are infinitely many elements between t minus epsilon 1 and t, there is at least one element which I can select, and that element is going to have some index n1. It's going to have some index n, and that's the first element I'm going to choose, so that will be my n1. That's the first n that I chose. Okay, so next I'm going to do something similar to what I did in the previous theorem. I'm going to make epsilon 2, the new epsilon, to be a minimum of t minus Sn1, so the distance between t and the first element I chose, and 1/2. Well, because it doesn't matter what epsilon 2 is, the set still has infinitely many elements, then once again I should be able to choose an element which belongs to t minus epsilon 2 and t, right, to the interval between t minus epsilon 2 and t. And I can label this index of that element as n2. Right, so for example, if I chose, I don't know, if n1 is 5, that means that S5 was between t minus epsilon 1 and t. So here maybe Sn2 is going to be, I don't know, 21. So S21 lies between t minus epsilon 2 and t. Doesn't have to be 21. The point is just that I should be able to select an index such that the corresponding element is between t minus epsilon 2 and t. Okay, so now I remember what my epsilon 2 was, right? It's a minimum of t minus Sn1 and 1/2. So I'm just taking this set of inequalities and I simply replace epsilon 2 by what it is. Okay, so then what am I doing here? I'm taking a minimum of two numbers, t minus Sn1 and 1/2. If t minus Sn1 is a smaller of the two, that means that this is going to look like t minus Sn1, and I'm going to get just Sn1. And if 1/2 is a smaller, and if t minus Sn1 is, as I said, if it's the smallest of the two, then 1/2 is going to be larger. So t minus 1/2 is going to be smaller than Sn1. And so then I can conclude that I have two inequalities. One is, so Sn2 less than t, right? That is automatic. That's the way I chose Sn2. But then if I have 1/2 as a minimum, I get t minus 1/2. If I have t minus Sn1 as a minimum, I get Sn1 on the right hand side. And because I'm using the minimum, then actually both of these inequalities will have to be satisfied at the same time. Okay, and so then again, I'm going to continue by induction. I want to prove now similar statements for any k. So what does it mean? It means that, so here I have 2, here I have 2. I'm going to suppose that Sn k is still less than t and bigger than t minus 1 over k, right? So it's t minus 1/2 here, t minus 1 over k. And I also want Sn k to be bigger than the previous Sn k minus 1, just like Sn1, Sn2 was bigger than Sn1. And I want everything to be still less than t. So I'm going to suppose that this is going to work at the kth level, and I just want to use induction to prove the same thing at the k plus first level. And I'm going to repeat exactly the same step as I did in the second case. What I do in the second case, I took a minimum of t minus Sn1 and 1/2. So now I need to take a minimum of t minus Sn k and 1 over k plus 1, right? For my epsilon k plus 1. And once again, because epsilon k plus 1 is just going to be some number, by my assumption, this set will contain infinitely many elements. Once again, right, because for any epsilon, I assume that this contains infinitely many elements. And so then I can choose an element with the index nk plus 1, which will be between these two guys, right? Again, if I have infinitely many elements of my set between two numbers, then I can always choose at least one of them between those two numbers. Well, and then same thing, I can recall what the definition of epsilon, actually it shouldn't be epsilon 2, it's epsilon k plus 1 here. So once again, what we have is a t minus this minimum, right? So if I take t minus this guy, it would be t minus t plus Snk. So we have that Snk plus 1 must be bigger than Snk. And likewise, it should be bigger than t minus 1 over k plus 1. So we have that. And so then by induction, we proved, right, that the same inequalities that were valid at the kth level are still valid at the k plus first level. And so then by induction, we constructed a sequence which satisfies this inequality for all k. right? So inequality like this for all k. But then I see that if I let k go to infinity, right, t is a constant, so it will converge to t. T minus 1 over k, when k goes to infinity, will converge to t as well. So s and k is less than something that goes to t, and is greater than something that goes to t. So limit of s and k must be equal to t. There is no other choice. And then from here, right, from the second statement, I know that s and k is always less than s and k plus 1. So as k increases, the sequence also is increasing. So that means that s and k must be monotone increasing. And that concludes the proof. Now, one comment here. Let's just try to visualize what we just did. So I'm trying to show that I have a subsequence that converges to t. And I know that if I pick any subinterval that starts somewhere and ends at t, any interval like that will contain infinitely many elements. Okay, so then I start with an interval from t minus 1 to t. It should have infinitely many elements. And because it has infinitely many elements, then I can pick some element which belongs to that interval. Okay, so then the next step, I'm going to take t minus 1 half, and I will try to find now an element which is going to be a new element of my set, of my sequence, which is going to be larger than Sn1 and t minus 1 half. Well, once again, what is the largest of these two numbers? In this case, it's going to be t minus 1 half, right? Then on the interval from t minus 1 half to t, once again, I know that I have infinitely many elements. So that means that I should be able to choose one element which is going to be in this interval, one element of my sequence, and I'm going to call that element Sn2. For the next step, I'm looking at Sn2 and t minus 1 third. Out of these two numbers, again, I can select the largest, so in this case, Sn2 is a larger number. And above those, I should be able to, again, on the interval from Sn2 to t, I have infinitely many elements still. So that means I can select Sn3 like this, right? Which is larger than Sn2 and t minus 1 third. And you see that I can continue doing this, and as I continue doing this, I am putting my Snk always in the interval from t minus 1 over k to t. So as k goes to infinity, Snk must go to t. And the way I'm constructing this subsequence also, I always choose Snk strictly to the right, or Snk minus 1, so that means that I'm getting a sequence which is monotone increasing. So this is just an illustration of this fairly lengthy proof that I just did. If you understand the illustration, then by going again through the proof, you should be able to follow what I'm doing. And we'll continue next time.